In the last class, we discussed about the practical transformer. We looked at the features of the ideal transformer. We saw that the ideal transformer required features like infinite permeability, infinite saturation flux density, hysteresis loop area should be 0, resistivity of the core material should be infinite, and of course, the resistivity of the coil, that the winding that is coiled around the core should also be 0. So, that there are no copper or core losses in the core. Now, we saw that the practical transformer has all of these features which are not which are finite, and therefore, there will exist core losses, and there will also exist a finite permeability, and because of this we included in the equivalent circuit of the ideal transformer extra 2 elements, one element called the RC, which represents the core losses, another element called the XM, which represents the magnetizing inductance, which means the current needed to magnetize the transformer. In the case of the ideal transformer, there was no current needed to generate the flux. So, today we will go ahead and introduce the other non-idealities, other imperfections to the ideal transformer, and see how the overall equivalent circuit would look like. So, till now we have an ideal transformer, so we have 1:n, and to this ideal transformer we have put a resistance RC in parallel and also an inductance which gives an inductive reactance XM. So, to the primary we connect a source, an AC source EG, and the induced EMF is E1. There is a current I naught which is flowing, and through the core loss component there is a current I C flowing, and through the magnetizing inductance there is a current I M flowing, and through the ideal transformer I is equal to 0 if there is no load connected across the secondary, and what you have here is E2. Now, at this point let us formalize some notations. We have been interchangeably using uppercase for the voltages, lower cases for the voltages, upper cases for the currents, and lower cases without being very consistent till now. But actually we have the lower cases, that is E1, E2, EG, I naught, IM, so on, would imply instantaneous values. So, the instantaneous values, you draw the vector diagram. And if we are drawing the phasor diagram, we said that the values of the vector represent the RMS values, the root mean square value or the effective values of the quantities. So, we shall use the notation with uppercase for effective values. I naught for the RMS values, IC for the RMS value, IM for the RMS magnetizing current, E1 as the RMS value of the effective value of the induced EMF, EG effective value of the applied generated voltage or the generator voltage. So, therefore, E1, E2, EG, I naught, IC, IM, so on, they would represent the RMS or effective values. So, from now on, as we are going to draw a phasor diagram in almost all the circuits that we will be discussing in future, we will try to use these uppercase notations for the RMS and the effective values, and therefore, the diagram would be phasor diagram, and if we use the instantaneous value, then those diagrams would be called the vector diagram. Okay, now coming back to the transformer, we have the transformer, the ideal transformer. This is the ideal transformer, and to the ideal transformer we have attached two components, the core loss component and the magnetizing inductance component or the magnetizing reactance component, which indicates two non-idealities. One is the loss, that is, there exists a finite hysteresis loop area and there exists eddy current losses, which means finite resistivity, and the other one is the XM, which draws a magnetizing current, which means to set up a flux in the core, some amount of magnetizing current has to be drawn from the source, and it is a reactive power that is being drawn from the source, and therefore, the magnetizing reactance XM. Now, we shall introduce a few other non-idealities. What is called the leakage component. In the transformer. So, to understand this, let us first take again an ideal transformer, and the ideal transformer on the core on our normal rectangular core. Let me show the rectangular core like that, and we have the primary windings, as shown. We also have the secondary windings, wound on the same core, as shown like this. This is the primary and the secondary. We have N1 number of turns in the primary, and we have N2 number of turns in the secondary. Now, to this we shall attach a generator to the primary, which is having an effective value E g, and there is an induced voltage with an effective value E 1 across the coil. This being an ideal transformer, if there is no load connected here and if there is a generator which is applied, even with I is equal to 0, even with I1 which is equal to 0, there is going to be a flux generated in the core, and that flux generated in the core is something like that. So, we have the flux that gets generated in the core. Now, if there is no load here, I2 is equal to 0. Now, there is a flux generated in the core and it is going to link with the secondary, which is going to generate a secondary induced EMF. Now, this flux phi 1 m, let us say, during no load, let us say 1 m 0. Now, this flux phi 1 m 0 is generated because a voltage source is generator is attached to the primary, and as I is equal to 0, there is no ampere turns, Ni is 0. So, there is no ampere turns to generate flux in the air, and therefore, all the flux is only in the core because the permeability is infinite in the ideal case, and therefore, all these flux link with the secondary, and it is going to produce a voltage at the secondary which is equal to 4.44 F N2 phi 1 m 0. This is the amount of voltage that is going to get introduced or induced in the across the secondary windings. Now, on the application of the secondary load, a whole lot of things changes. The moment we apply the secondary load, there is going to be a secondary current I2, there is going to be a primary current I1 which is not 0, and these will induce a complex set of fluxes which interact with each other, and let us see what happens. So, first let us introduce a load. So, let me now introduce a load on the secondary side. Now, because a load on the secondary side has been introduced, Z2, there is going to be a secondary current which is not 0, and as a consequence there is also going to be a primary current which is not 0. So, the fluxes here are now N1 I1 is going to generate phi 1 m. This is generated by N1 I1, but there is also a possibility that some of the fluxes just loop back through the air like that. Some of the flux is going to go through the core and some of the flux is going to loop back through the air, because now there is a finite Ni which can drive the flux through the air which has a lower permeability. Now, this flux we will call it as the leakage flux, which is not linking with the secondary. Let us call that one as phi sigma 1. So, in actuality N1 I1 is producing flux phi 1, but this phi 1 is having two components, phi 1 m and phi sigma The phi 1 m component is called the mutual component, which links with the secondary winding. It is flowing through the core and links with the secondary winding. Phi sigma 1 is called the leakage component, and this does not link with the secondary. Now, because there is a flux phi 1 m flowing through the secondary, there is going to be a induced EMF in the secondary, and that is going to be E2, and that is driving a current I2 through the load. Now, there is an ampere turns N2 I2 due to the fact that there is current flowing in this winding, and this N2 I2 is going to give you an opposing flux in the core. Reason being that in the primary the power is flowing into the core, in the secondary the power is flowing out of the core. So, we have an opposing flux which is flowing in the core material as shown like this. It is flowing in the opposite direction. There is an opposing flux N2 I2. Now, this flux we call it as phi 2 m due to N2 I2. But phi 2 m is the flux that flows through the core, links with the primary also. But this also produces some ampere turns which pushes some flux through the air here, and it has a path something like that, and this is called phi sigma 2, and this is the leakage component of the flux due to N2 I2 ampere turns, and this phi sigma 2 does not link with the primary, only phi 2 m links with the primary. So, therefore, we can from this simplify the flux pattern slightly. By rewriting our transformer with its primary and secondary windings. This is the primary winding, this is the secondary winding, which is connected to the load Z2, There is a current I2 which is flowing here, there is a current I1 which is flowing here, and there is a voltage source with effective value Eg and induced value E1, Eg equal to E1, which is, now this is having N1 turns and this is having N2 turns. Now, here let us have the equivalent flux in the core, which is flowing like this, and we shall call that as phi m. The equivalent flux in the core, see, we have phi 1 flowing in one direction, phi 2 flowing in the opposite direction. The equivalent flux phi 1 m minus phi 2 m vectorially would give you phi m, and this is called the mutual flux, let us say. And in the primary we saw that N1 I1 is producing flux phi 1, which has two components, phi 1m and phi 2m, phi 1m and phi sigma 1. Phi 1m is the mutual component, phi sigma 1 is the leakage component. There is a leakage component here. So, we have a leakage component of the flux phi sigma 1. Likewise, on the secondary for N2 I2 ampere turns, phi 2 is produced and this has two components, phi 2m and phi sigma 2, the leakage component. So, the leakage component is not linking with the primary, and that is what we are going to show here. This is phi sigma 2. So, you have three fluxes, the primary leakage flux, the secondary leakage flux and the mutual flux which links both the coils together. So, if we look at even the induced voltages at the primary and the secondary, now the secondary induced voltage is composed of two components. The voltage due to the mutual flux which links the primary and the secondary phi m, which is 4.44 N2 F phi m. That is one component which is due to this flux. And then there is, and we call this one, let us say E2, just E2 due to the mutual flux. Then there is the other component which is due to the leakage flux here phi sigma 2, which is also linking the N2 coils, and that would be, let us say, E sigma. Let me just rename this as E mutual on the secondary side, E leakage sigma on the secondary side, the voltage across the leakage voltage induced due to the leakage flux, which is 4.44 into N2 F phi sigma 2. Now, of course, these two fluxes are not necessarily in phase, and therefore, these two voltages are also not in phase. So, it is vectorially they will add up to obtain the E2 across the secondary. Likewise, the primary side also you have two components which are producing the induced EMFs. One component 4.44 N1 now F into phi m. This is the voltage that is induced due to the mutual flux flowing in the core, which links both the primary and the secondary. And the other component, which is 4.44 N1 F phi sigma 1. This is the voltage induced due to the leakage component of the flux, which is linking only N1 and not N2. So, these are the voltages that get induced due to the various fluxes. Now, we can reconstruct or construct the equivalent circuit by up by probably looking at these voltages. We know that E1 is the vectorial sum of the induced EMF EM1 and E sigma 1, which is the leakage component. Likewise, in the secondary also it is the vectorial sum of EM2 and E sigma 2, the leakage component. So, how does it look in the equivalent way? So, what we can do, this flux here, which is phi 1, which is containing both the mutual and the leakage, can be split into two windings, one which links with the secondary, that would be the ideal transformer, the other which does not link with the secondary, but still there is a flux. So, we shall reconstruct it in this manner. Let us have the transformer here, and let us have this windings, primary and the secondary. As shown here. Now, this has N1 and N2. Now, here there is a current which is flowing through this coil, and this N1 I1 is going to produce a flux phi m in the core. So, let us say this is an ideal transformer, which means that all the flux is flowing through. Now, let us have a virtual coil here, also N1 turns, but of course, the flux is now flowing through the air. So, there is going to be a flux here equivalently, let us say, flowing through the air, due to the fact that there is a current flowing through this coil and this coil, the same current flowing through this coil and that coil. And that is going to induce a EMF, which is E sigma 1, due to the leakage flux phi sigma 1, because a current I1 is flowing through the coil. So, this is an equivalent coil which is just producing the leakage factors, that is, it is producing the leakage flux, this is producing the voltage which is being induced due to the leakage flux E sigma 1, and this is producing EM1. The primary side induced EMF due to the mutual flux which is linking both the primary and the secondary coils, and this flux of course is called phi m mutual flux. So, if I complete the primary portion of the circuit, you have the generated. So, there is the generator here which has a effective value of E g. Now, similarly on the secondary side, there was a flux due to a current I2 flowing in the N2 coil, which produced a flux phi sigma 2, and this flux phi sigma 2 will produce E sigma 2 as the induced EMF due to the leakage flux, and we have EM2, the induced EMF across the coil due to the mutual flux. And on completing the circuit, here we have the load Z2, and this would be the terminals of your transformer. This is going to be E2 and this is of course E1. So, now what we have done is we have brought out the leakage fluxes and that component of the reactance which is actually the voltages that are induced due to the leakage fluxes out on both the primary side and the secondary side, and therefore here you have X sigma 1, the leakage reactance on the primary side, which is equal to E sigma 1 by I 1, E sigma 1 by I 1, and on the secondary side the leakage reactance is equal to E sigma 2 by I 2. Now, there is one more non-ideality to add, and that is the winding resistances. So, the windings, the coils which are wound on the core here, they are physical wires made of copper or aluminum, and therefore, they have finite resistances. So, depending upon the length of the wire, the value of the resistance can be fixed or measured, and that is going to be in series with the coil, and the coil themselves in the ideal transformer can be assumed to be having 0 winding resistance. So, which means we bring out here the resistance of the coil, and say that this is R1, and then we bring out the resistance of the coil, the secondary side, and that we call it as R2. So, R2 is the coil resistance of the N2 turns, R1 is the coil resistance of the N1 turns. Now, this transformer here we said was ideal, but if this transformer, this portion of the transformer, this is now considered to have the imperfections of the core loss and the magnetizing inductance, then the equivalent circuit what we discussed in the last class would come into place in this portion. So, the entire equivalent circuit can be written in the following manner. So, we have a source with generator voltage E g, and this source is connected to the terminals of the transformer, and this would be E1, the terminals of the transformer. Now, from the primary side terminals, if we go, you have first R1, the winding resistance, and then we have an inductance which is going to give an inductive reactance L sigma 1, the leakage inductive reactance on the primary side, and then further going down we have two components that we discussed in the last class, which is the core loss component and the magnetizing inductance component. Core loss component and the magnetizing inductance component, Xm and Rc, and this goes into the primary of the ideal transformer. The secondary of the ideal transformer contains the leakage reactance of the secondary. This is followed by the resistance of the secondary coil, N2 turns, and that gets terminated as the secondary terminals, and there we have the load across the secondary terminals. So, this would be our secondary. So, if you see here 1, 2, 3, 4, this is the practical transformer. So, if I draw this red enclosure here, the practical transformer which has terminals 1, 2, 3, 4. This portion is an ideal transformer. So, the practical transformer is composed of the ideal transformer plus non-idealities which are represented in terms of circuit elements, that is the leakage reactances X sigma 1 and X sigma 2, magnetizing reactance Xm, core loss resistance Rc, primary side coil winding resistance R1, secondary side coil winding resistance R2. So, this would be a practical transformer, and actually to you what will be available is the terminals 1, 2, 3, 4, everything else is a black box, and all these are embedded inside the transformer which are not available to you as physical quantities. However, the values of these can be obtained through some measurements which we will discuss much later, but for now this would be the complete equivalent circuit of the practical transformer. So, then we have to define the currents. So, we are taking a current from a source. We are taking a current from the source, we will call it as I1, and there is a current flowing in the secondary, it is called I2. So, now I1 flows through the primary leads into the transformer, it gets split here as I0 and it goes through here as IP, ideal, I primary ideal, and on the secondary side you have the current I2 which is flowing through, and here you have IM, the magnetizing component, IC, the core loss component of the current. And voltages wise, this voltage will be EM1, this voltage is E sigma 1, and this voltage is E1 which is across the terminals of the transformer. Likewise, this voltage is EM2 and this voltage is E sigma 2 and there is a voltage here which is I1 R1, there is a voltage here which is I2 R2, which defines completely the equivalent circuit of the practical transformer. Now, let us take a simple example to consolidate what we have done till now. Okay. The secondary winding of a transformer, has 180 turns. So, under load, meaning when the secondary side is connected to a load Z2 under loaded condition, the secondary current I2 effective value, always effective value, is 18 amps. The phi m, which is a mutual flux, is 20 milliwebers. The secondary leakage flux phi sigma 2 is is given to be, let us say, 3 milliweber. And the frequency of the generator is 50 hertz. We are applying a 50 hertz frequency. Now, these are the specifications given for a particular transformer. Let us find first the voltage induced in the secondary by the leakage flux as the first step. Let me So, what is the voltage induced in the secondary? We know that E sigma 2 is given by 4.44 N2 into frequency into flux sigma 2, phi sigma 2, which is 4.44 into 180 turns into 50 hertz into 3 milliwebers, which is 0.003 webers. So, that would be 119.9 volts or approximately 120 volts. So, 120 volts is induced due to the secondary leakage. Now, let us put the second question. What is the value of secondary leakage reactance? So, the secondary leakage reactance is given by the voltage induced due to the secondary leakage reactance divided by I2. If you go back, you see that the secondary leakage reactance X to the E sigma 2 by I2. Now, which is equal to, and we obtained E sigma to be around 119.9 volts divided by what is given is around 18 amps, which is flowing through the secondary, and this is around 6.66 ohms. Let me put a third question to the same problem. What is the voltage induced by the mutual flux? What is EM2? The voltage induced by the mutual flux phi m. So, EM2 is equal to 4.44 into N2 into F into phi m, and this is 4.44 into 180 turns into 50 hertz into phi m, which is 20 milliwebers, 0.02 webers, and this is 799.16 volts or approximately 800 volts. Okay. Just to give you a feel for the number and what you want to do when you start calculating. Of course, we will take up few more examples later on. Now, the next topic that we need to have a look at is the issue of the power that is getting transferred. So, the power that is getting transferred from the primary side to the secondary side is the VA, the apparent power. The transformer has to be rated for the apparent power, even though only the active component of the power is what is given to the load. The reactive component again flows back, but still that component has to be handled by the transformer. The reactive component emanates from the primary side, goes through the transformer and also comes back to the primary side. It is regenerative or the reactive component, but the transformer has to handle that power. So, if there is a completely reactive load, meaning if there is a reactive load of 1000 VAR and if there is a resistive load of 1000 watts, in both the cases the transformer has to be rated for 1000 VA, because that 1000 VA is what it has to handle, and the heating value of the transformer is actually related to the apparent power. because whether it is the reactive load or the active load, the transformer has to undergo so many cycles, which means so many traversals of the hysteresis loop, and also the eddy currents in the transformer does not distinguish between the reactive load and the active load, and therefore, the heating in the transformer is related to the VA or the apparent power that is flowing through the transformer, and therefore, the nameplates of the transformers are rated in terms of VA rather than watts. So, this is one issue. So, if you take a example, let us say a nameplate of a transformer. So, a transformer nameplate of distribution transformer. So, high power transformer indicates that it is a 250 kVA transformer, 50 hertz, primary has 4160 volts rated, secondary has 480 volts rated. Now, this is the specification of the transformer. So, first one, let us say what is the nominal primary and secondary currents. So, the nominal current of the primary, that is I1, is given by the VA rating divided by the nominal E1 of the primary, which is 250 into 1000 VA divided by 4160 volts, which gives you 60 amps. Likewise, the nominal rating of the secondary is the VA rating, which is the same for both the primary and the secondary, by the nominal secondary voltage E2, whatever it is rated. So, that is 250 into 1000 VA divided by 480 volts, which turns out to be 521 amps as a VA rating. Now, suppose for this transformer, which is rated at 4160 volts, we apply instead just 2000 volts is applied. 2000 volts is applied. Under such conditions, can it give the same VA rating? That is the question. Now, if we take the transformer, we are applying a voltage which is lesser than the primary, which means the volt second is smaller for the same frequency, which means the operating point in the BH curve is going to be smaller. So, a smaller BH loop is going to be traversed. and therefore, the transformer is going to run cooler. However, if we have to get the same VA, if I have reduced the voltage to have the same VA, if you reduce the voltage, the current has to be increased proportionally to have the same VA, which means the I square losses would increase square times, and the windings may not be rated to handle the doubled or the increased current, because the losses are going to be I square times, and therefore, the windings or the coil of the transformer which is wound in the core can handle only the nominal current rated for what it is rated, which means 60 amps for the primary and 521 amps for the secondary. Therefore, if I apply 2000 volts, then the VA is 2000 volts into 60 amps, which is 120 kVA. So, to a 250 kVA transformer, if you are applying a lesser voltage, do not expect that it will deliver the whole 250 kVA, because it cannot handle the increased current, because the windings will not be rated for the increased current, and therefore, you have to limit the current only to the nominal currents, which is the 60 amps, and therefore, the nominal current into the reduced voltage will give you the apparent power, which is going to be considerably reduced with respect to the rated. Now, having discussed the practical transformers and having developed the complete equivalent circuit of the practical transformers, which contains 3 reactances: the magnetizing reactance Xm, the leakage reactance X sigma 1 and X sigma 2, the primary and the secondary leakage reactances, and contains 3 resistances: Rc, which is the core loss component, R1, which is the winding resistance of the primary coil, R2, which is the winding resistance of the secondary coil. All these are put together along with the ideal transformer results in the practical transformer. Now, to this practical transformer, the various loads and voltages are applied, and with different power capacities. In the next session, we shall discuss about the impedances and the values of these practical components that we introduced in the practical transformer, how to obtain them, and also about the per unit impedances, which will give a much better understanding of the transformer. We shall discuss all these things in the next class. Thank you for now.